neural encoding and auditory processing of electrical stimulation in cochlear implant users. So this slide illustrated how cochlear implant works in general. The electrical array is implanted in the cochlea. The electrical stimulation sent by CI electrode directly stimulates the cochlear nerve. The information encodes and processed by the cochlear nerve then will be processed by higher neural structure of the auditory system before it can be understood and interpreted by CI users. So even though cochlear implants has been used to restore auditory function in hearing impaired listeners for more than 5 decades, we are still facing the same two major issues that have been identified early on. First, there are substantial variabilities in speech perception outcomes among cochlear implant users. Second, the majority of CI users still have difficulty in understanding speech in competing background noise. As a result, there's no evidence-based clinical practice for optimizing program settings or predicting cochlear implant outcomes for individual patients. These two issues are clearly illustrated by the CNC word score and the AZ-Bio sentence score measured in quiet and in noise that has been reported by Waller et al. In 2022. So our lab takes a bottom-up approach that includes multiple objective and behavior assessment to identify factors accounting for variations in speech perception outcomes and deficits in speech perception in noise among CI users. Our rationale for taking this approach is that the cochlear nerve is the first neural structure that receives electrical stimulation from a cochlear implant. Therefore, how well the cochlear nerve can faithfully encode and process electrical stimulation can be the bottleneck for cochlear implant clinical outcomes. Before we talk about the results of the research studies, I would like to provide some background information about the cochlear nerve fibers in human listeners. As I mentioned previously, these fibers are the direct and only target of the cochlear implant. Therefore, the condition, the number, and the responsiveness of these surviving nerve fibers fundamentally decide the quality and the quantity of the information that can be sent to the brain. As shown in this diagram, the human auditory nerve fiber is a primary bipolar neuron. It has three main components: a peripheral axon, the soma or cell body, and a central axon. The peripheral axon is a part of the neuron that travels from inner hair cell to the cell body. Its most peripheral part is the myelinated terminal, which forms the synapse of the hair cell. Away from the terminal, the axon is myelinated, but its insulation is broken by the nodes of Arabia. These nodes are key sites where electrical stimulation can trigger the electrical responses. The soma or the cell body is almost entirely unmyelinated. This is a major difference from any other species, including primates, whose cell body are myelinated, and it has significant consequences for how the neuron responds to electrical stimulation. The central axon is the final component of the neuron. Compared with the peripheral axon, the central axon is thicker and more heavily myelinated, which allows it to send signal more rapidly. So regardless of the reason, cochlear nerve fiber degeneration is a typical dying back process that is known as retrograde degeneration, which start as a peripheral and move more centrally toward the cell body. As the diagram illustrated, this process can often begin with the synapse, the loss of synapse, and the retraction of the peripheral axon. And then the remaining axon then undergo a slow atrophy with myelin self-thinning and a reduced axon diameter. Eventually, the entire peripheral axon gets lost, leaving only the soma and central axon intact. This stage where the cell body and the central axon survive can last for decades in human listeners. However, this monopolar neuron may also eventually die and leading to a complete degeneration of the entire cochlear nerve fiber. CN fibers with all highlighted cochlear nerve fiber with all highlighted status can exist in cochlear implant users. And all of them can be activated by electrical stimulation from the cochlear implant. However, there's substantial variations in terms of the degree of degeneration among CA fibers across cochlear implant users, as well as across different cochlear regions within individual CI users. There are still no measurement that can evaluate the degree or the type of degeneration for each individual patients. So the primary measure used in our study to evaluate the cochlear nerve function or responsiveness is the electrical evoked compound action potential, which can be recorded using CI electrode with commercial software provided by CI manufacturers. This is what the ECAP look like in a typical adult CI user. So the ECAP is a near-field recorded neural response generated by cochlear nerve. Its presence depends on the existence of sufficient cochlear nerve fiber responding synchronously to electrical stimulation. The ECAP is also affected by the electrode-related factors as well as the electrode to neural element distance. So several patient populations were tested across our studies. They were selected based on the health status of the cochlear nerve, which has been characterized by histological results of human temporal bone studies or the electrophysiological studies. The first patient population is children with cochlear nerve deficiency, or CND. CND refers to a small or absent cochlear nerve as determined based on MRI scans. They represent a patient population with fewer but otherwise healthy cochlear nerve fibers, with more cochlear nerve fibers locating toward the basal region of the cochlea. So the second patient population is children with gap junction beta-2 genetic mutation. They represent a patient population with minimum neural damage in the cochlear nerve. The third patient population is children with auditory neuropathy spectrum disorder. They are the patients with poor neural synchrony that cannot be fully compensated for by the enhanced neural synchronization provided by the electrical stimulation. Then the fourth patient population are the postlingual adult CI users. They represent a patient population with reduced cochlear nerve fibers and substantial peripheral axon loss in the basal cochlea. So the first study I will discuss is about the electrodo-neural interface. It was first defined by Dr. Julie Beer in 2010. It was defined as the effectiveness at which each cochlear implant electrode stimulates its target cochlear nerve fibers. The rationale for us to study the electrodo-neural interface is that if the cochlear implant electrode cannot effectively stimulate the target cochlear nerve fibers, there won't be enough information transmitted to higher auditory structure for speech perception. Prior to our study, psychophysical tests such as auditory detection threshold for focused electrical stimulation were used to investigate the electrodo-neural interface. Unfortunately, this test cannot be applied across CI devices or patient populations. If we list the factors affecting the electrodo-neural interface with those affecting the ECAPs, they are actually the same set of factors. Therefore, we think the ECAP results can be used as a functional readout for the quality of the electrodo-neural interface. Well, the first two groups of factors can be easily measured or determined. The functional status of cochlear nerve, it's a challenge, and we need to define the parameters for the parameters that can be evaluated for this purpose. To partially address this challenge, we compared ECAP results recorded in children with cochlear nerve deficiency with those recorded in children with idiopathic sensorineural hearing loss. Our results show that children with cochlear nerve deficiency, which is a patient population with fewer but otherwise healthy cochlear nerve fibers, had increased the ECAP threshold, reduced the ECAP amplitude, flatter ECAP input-output function, longer N1 latencies, and prolonged recovery from the absolute refractoriness. Therefore, we selected these ECAP parameters as biomarkers for poor functional status of the cochlear nerve due to reduced number of healthy CN fibers. So after those biomarkers got identified, we collaborated with Dr. Xia Ning, the Chief of Artificial Intelligence Health at the Ohio State University, and used the machine learning technique to generate predictive models. These models generate an index based on ECAP results to quantify the quality of the electrode neural interface. We gave this index a very boring name, the ENI index. So after the model was created, we further refined them to evaluate the electrode neural interface for individual electrode site. This slide shows the electrode-specific ENI indices for group of children with cochlear nerve deficiency and their matched peers with idiopathic sensory neural hearing loss. All participants use a cochlear nucleus device in their test year, and I should make it clear that all of the patients we test in our study use a cochlear nucleus device. This is a major manufacturer that used got implanted at our institute. So these results clearly show overall the ENI indices measured in children with CND, which is indicated using the black triangles, are smaller than those measured in children with idiopathic sensory neural hearing loss, which indicate worse electrode neural interface in this case. More importantly, the ENI indices measured in children with CND generally followed a base to apex decreasing pattern, which is consistent with the distribution pattern of their available cochlear nerve fibers in the cochlea. So as a part of the model validation process, we studied the correlation between the ENI indices generated using all three analytical models with the constant nucleus constant or CNC Wurtz score measured in quiet in postlingually deaf adult CI users. There were significant correlations between the results of these two measures, regardless of analytical model that were used to generate the ENI index. It is important to note that we selected these ECAP biomarkers based on results of unique patient population who do not have much damage in their existing cochlear nerve fibers, which is a primary limitation of our models. This limitation raised one important question: does the ENI index capture all important aspects of cochlear nerve responsiveness for speech perception across different cochlear implant patient populations? To answer this question, we evaluated the relationship among ENI index and several temporal response properties of the cochlear nerve that have been shown to be important for speech encoding based on animal data, as well as their association with speech perception scores measured in both quiet and noisy adult CI users. The temporal response property included in this study include the spatial neural adaptation and the recovery from the neural adaptation induced by prior stimulation, as well as the sensitivity to amplitude modulation cues. The size of the dot shows on this figure indicate the strength of the correlation among these parameters, and so there are really no significant correlation as shown in our statistical analysis results. So then let's look at their correlations with the CNC Wurtz score measured in different listening conditions. And there are two observations we can make based on these the results. The first observation was that the amount of variance in CNC Wurtz score explained by these CN response properties increased from 20% to 53% as the challenge of listening, as the difficulty of listening condition increased. Second, the ENI index and the speed of the adaptation recovery are the two parameters explain the variance in CNC Wurtz across all three listening conditions. So this observation also applies to the results of the AZ sentences in general. Overall, the results show that the response property of the cochlear nerve to electrical stimulation are more important for speech perception with the CI in noise than they are in quiet. In addition to the ENI index, the speed of recovery from neural adaptation is the most informative predictor for speech perception performance in CI users. So previous studies have shown that the faster recovery from neural adaptation were proposed to be important for producing peaks in the discharge rate of the cochlear nerve, which enhance the representation of the temporal information of speech. Better sensitivity to temporal envelope cues, as indicated by temporal processing acuity, has also been associated with better cochlear implant outcomes. So based on this theories or literatures, then it raises the question: does the faster adaptation recovery lead to improved temporal processing acuity? To answer this question, we conduct another study. Okay, sorry. To answer the question, we use a within subject design for each of the, sorry, my mouse have some issues. For each of the 14 years tested in 11 adult participants, we measure within channel gap detection threshold, which is the assessment of temporal processing acuity at 2 electrical locations with different speed of recovery from neural adaptation. The speed of adaptation recovery was quantified using a parameter called tau3, with the larger tau3 values indicate faster adaptation recovery. The within channel gap detection threshold were evaluated using both psychophysical procedures as well as electrophysiological measure of the auditory evoked potential. So the stimulus we used to measure the cortical auditory evoked potential was trains of electrical pulses with a duration of 800 milliseconds that were delivered to individual CI electrode. A schematic illustration of the stimulus shown at the bottom of this slide. A temporal gap with a duration ranging from 0, which means no gap, to 64 milliseconds was inserted after 400 milliseconds of stimulation. So the top row shows the responses we recorded from all 14 years. Each gray line, each dark gray trace represents the response recorded in each test year. The black trace represents the group average. The blue rectangles indicate the onset and the offset response evoked by the pulse trend, and the red rectangle indicates the responses evoked by the temporal gaps. The shortest gap duration that evoked this response was defined as the objective gap detection threshold. So our results showed a significant correlation between gap detection threshold measured using these two assessments. Therefore, I will only use the results measured using psychophysical procedures to show the final results of this specific experiment. So just as we mentioned before, we are expecting to get a shorter gap detection threshold from the electrical locations where the cochlear nerve fibers show a faster recovery from neural adaptation, as indicated by larger tau3 values. And these are our results. So there's no consistent trend that align with our expectations. So this is the result do not support this our hypothesis. Then this negative results made us reconsider our research question and study design. And then we realized there's a big missing piece in the field of cochlear implantation. So let's revisit the slides and discuss what this damage means for cochlear nerve responsiveness. The animal study showed that the myelin self-thinning and reduced axon diameter result in changes in cell membrane properties. The loss of peripheral axon also changed the action potential initiation site to the central axon. These issues increase both the temporal jitter in the spiking firing of individual CN fibers as well as the discharge synchronization among cochlear nerve fibers. Both factors result in decrease the neurosynchrony in the auditory nerve. So in acoustic hearing, the neurosynchrony in the auditory nerve has been shown to play an important role in determining temporal processing acuity and speech perception outcomes in noise. However, due to the lack of non-invasive tools for assessing it in CI users, it has never been evaluated in electrical hearing. As a result, the characteristic of the neurosynchrony in the cochlear nerve in CI users remains unknown. Its association with the auditory perception outcomes in human and the patient also remains unknown. So to address this critical knowledge gap and scientific needs, we collaborated with Dr. Ian Bruce at McMaster University and developed a method to evaluate neurosynchrony in the cochlear nerve in human CI users using an index called the face locking value. So in this method, 400 single trials of ECAP responses were recorded. The inter-trial phase coherence among these 400 trials was calculated as 6 linearly spaced frequency for 6 overlapped timeframes that include the entire recording window of the ECAP using FFT analysis. The average phase locking value across all frequencies and timeframes is used to quantify the neurosynchrony in the cochlear nerve. The top row shows the individual ECAP responses recorded at 4 electrode locations, as well as the average response, which is indicated in the black line at these locations. The bottom row shows the result, the heat map generated based on the results of FFT analysis. So the phase locking value is a measure of trial-to-trial phase coherence in the summed activity of cochlear nerve fibers evoked by electrical stimulation. It quantifies the degree rather than the time frame of neurosynchrony in the cochlear nerve. It represents both temporal jitter in the spiking firing of individual cochlear nerve fibers and the discharge synchronization among cochlear nerve fibers across multiple stimulation, which is a condition experienced continuously by cochlear implant patients. The phase locking value ranges from 0 to 1, with the larger value indicate greater neurosynchrony. Okay. So to validate this newly developed method to a limited degree, we compared the phase locking value measured between children with cochlear nerve deficiency and children with GGB2 mutations. Just a reminder, children with GGB2 mutation represent a patient population with minimum neural damage in the cochlear nerve. In addition to phase locking value, we also measure the interface gap effect or the IPG effect on the ECAP and compare between these two patient populations. The IPG effect has been shown to be indicative of the number of available cochlear nerve fibers responding to electrical stimulation. Based on the health status of the cochlear nerve in these two patient populations, we expect a significant group difference in the IPG effect due to the substantially less existing cochlear nerve fibers in children with CND, but a non-significant group difference in the phase locking value due to the good health of these existing cochlear nerve fibers in this patient population. So here's the results, and the blue symbols indicate the results we record from the children with CND, and the gray symbols indicate the results we got from the children with GGB2 mutations. As you can tell, for the IPG effect, which indicates the number of available cochlear nerve fibers, there's a significant group difference at all 3 electrode locations we measured. And if we look at the phase locking value, there's no group difference at any electrode locations between the 2 patient populations, which is consistent with our expectation. We also compared the phase locking value between children with auditory neuropathy spectrum disorder or ASD and children with GGB2 mutations. Luckily, we were able to recruit 2 ASD children with autofurling mutation, whose site of lesion were peripheral to the cochlear nerve. So they are not expecting to have a substantial damage in their cochlear nerve in these 2 cases. Based on the anatomy and the pathophysiology of these 2 patient populations, we expected a significant difference in the phase locking value between these 2 groups. Our results were consistent with our expectation. So the left panel shows the individual data of all kids who were tested in this study. The 2 out of 14 kids, the results are shown in red circles, open circles, and the red panel shows the means and standard deviations between the two groups. As you can tell, there is significant difference between the two groups, with children with auditory neuropathy spectrum disorder show smaller face lacking values across the electrode location we tested. And interestingly, with the children with the two children with autofurling mutations, their face lacking values fall within the range of the children, within the range of the results we measured from the children with GGB2 mutation. Okay. So finally, let's look at the results from post-lingually deaf adult CI users. And just a reminder, they are the patient group with substantial peripheral axon degeneration at the basal region of the cochlea. This figure shows the means and standard deviations of the face lacking value measured at 4 electrode locations across the electrode array in 24 adults CI users. As expected, the face lacking value measured at electrode 3, which is the basal electrode in cochlear nucleus device, was significantly smaller than those measured at electrode 9 and electrode 15. The 2 electrode locations located more toward more apical region of the cochlea. Overall, these results provide the evidence supporting PLV as an indicator of neurosynchrony in the cochlear nerve. So let's look at the relationship between the neurosynchrony in the cochlear nerve, which is quantified using the face lacking value and the auditory perception outcomes. First, we examined the relationship between the face lacking value and the gap detection threshold using both cortical evoked potentials and psychophysical procedures. This slide shows the cortical evoked potential elicited by different gap duration as indicated by the red triangle, at 2 electrode locations with different face lacking values in each of 2 participants. They are just 2 examples. The green lines represent the response recorded at the electrode location with a lower face lacking values, which indicate poor neurosynchrony. The red lines represent the response recorded at the electrode location with a higher face lacking value, which indicate a greater neurosynchrony. The gap duration used to evoke these responses are labeled for these traces. So in both examples, this data clearly show a better sensitivity to temporal gaps at the electrode location with better neurosynchrony. Okay, then let's look at the behavior data. So these results show the psychophysical gap detection threshold measured at 2 electrode locations with different face lacking values in each of 24 adult CI users. So smaller gap detection threshold were measured at the electrode location with a higher face lacking value in 20 out of 24 participants. Only 4 participants showed a different pattern. So it's worth it to point out that all except for 1 participant who were tested in the experiment evaluating the relationship between tau3 and the gap detection threshold were also tested in this experiment. The difference in study results is very apparent. Okay, so this slide shows the correlation between the CNC word score measured in quiet for children with auditory neuropathy spectrum disorder and children with idiopathic sensory neural hearing loss. There's a robust correlation between the results of these 2 measures for children with NASD only, which as we expected. Then finally, this is the relationship between the face lacking value and the AZBL sentence scores measured in quiet and in 2 noise conditions in 28 adult CI users. The significant correlation between the results of the 2 measures were observed for the SNR 5 dB noise condition. So overall, if we summarize based on the experiment I presented so far, the take home messages are the responsiveness of the cochlear nerve is determining factor for neural representation of the electrical stimulation in the auditory system. Neural synchrony in the cochlear nerve is critical for temporal processing acuity and speech perception in noise in implanted patients. Finally, how well the cochlear nerve encodes and processes electrical stimulation plays a vital role in determining CI clinical outcomes. So we are expanding our research to a new direction. Now we are interested in to study the audio-visual integration and cognitive load in CI patients. Specifically, we conducted a study to evaluate how CI patients can integrate the temporal cue delivered by visual input with auditory input for speech perception understanding in quiet and as well as in noise using F-near technique. And then how that were related with the peripheral input come from the auditory nerve. So this is a pilot study, and this is just published in Ear and Hearing. I'm not going to go too much detail with this study because again, the data collection is still ongoing. So I will acknowledge our funding sources. So the study will, presented today has been funded by multiple grant from NIH awarded by me, as well as from a research grant awarded to Dr. Ian Bruce from Canada. Okay, and I would also like to acknowledge my wonderful collaborators, Dr. Xiang. She's an AI expert at OSU, Dr. Ian Bruce. We collaborate with him to develop the face locking value measurement method. And Dr. Jacob Olison from University of Iowa. He conducted all the statistic analysis for our research studies, and Dr. Monita Chatterjee, who has been a long-term mentor for me and provide her expertise for the psychophysical measurement. Finally, I would like to acknowledge all of my lab members and as well as my lab alumni, and without them, we cannot finish this research projects. So that's all of my the content I would like to present. Thank you all.